Okay, welcome back, everybody. How was your Thanksgiving? Amazing? What makes Thanksgiving amazing? No school? Okay. Anything else? The food. Okay, yeah. I like Thanksgiving quite a bit. It's a time to get together and relax. And are you now done with your exams? Like some of you? No? Oh, so what are you studying for? Oh, that's on Thursday? What? Cal? Okay, all right. Well, good luck. Good luck with that. All right, so administratively, we'll pull up the syllabus just for a minute, just to show us where we are and the progress we're making. As you know, we had exam 2 last week, and today we're going to do session 22 on failure criteria, and we'll talk some more about failure criteria on Thursday as well. And then we kind of enter the home stretch, or we're almost in the home stretch. We have sessions 24 and 25 that will be talking about beams, essentially. And they're key concepts. We've talked quite a bit about the stresses in the beam, transverse shear stress, the bending stress, right? And finally, we'll get to figuring out what the displacement is. And you'll be able to use tables that you can find on the internet to do rough estimates for deflection and diffusions. And then the last day of class will be the 12th, and what we'll do then is just kind of have a review maybe, talk about things, maybe answer questions, embarrass myself, we'll see. But that's kind of what we're planning on. All right, any questions on this? Okay, all right. Wow, I didn't know that was a way to get everyone to be quiet by asking if there were questions. Yes?
Do you have office hours
Between the 12th, yeah, we can have office hours, sure. We can, I'm not sure which days those be, but yeah, I'll keep my normal office hours. Yeah. Okay. So I'll just keep my normal office hours until we have the big one. Okay, any other questions? Are you okay, Jesse? You're looking at me with this face. I don't know, I was getting a vibe. Alright. Okay. Alright, so let's go. If I can get this off. Okay. And we'll come over here. Alright, yes, we're in it. Okay, so today what we are going to review is a little bit about material testing and ductility. And we've talked about these principles already. It may have been a little bit a while ago, but you should be pretty familiar with them. And then we will talk about one criterion for deciding if something is going to fail. And that is using maximum normal stress. And it's particularly useful for brittle materials, although, as we will say multiple times today, when you're looking at brittle materials and you're thinking about trying to figure out if they're going to fail catastrophically, be generous with your safety factor. There's a lot of variability, okay? But nonetheless, we do have some guidelines and some principles, and maybe a little demonstration too. And then we'll get into maximum shear stress, which is applicable to ductile materials. Yes, Federico.
Does it happen to be the chalk, the demonstration?
Yes, it does happen to be the chalk. Have you seen this demonstration before?
I'll find out.
You'll find out. Okay, wonderful. All right. Thank you for foreshadowing our demo. So let's get into tensile testing, material testing, compressive tests. And if you had to think about this, what would you say is the purpose of characterizing a material in a material testing machine? Like, why do we do it? Yes, Kevin.
To see which materials are better suited for what kind of tasks and under what kind of loads and conditions.
Okay, so to see which materials might be suitable for the anticipated loads that we are going to have in our situation. Sure, okay. Other thoughts? More specific ideas? Why do we test materials? Yes, Federico.
To make sure they're safe when they're going to be used for their actual purposes. No one gets injured.
Right, so we're concerned about safety. Okay. And does this mean that if I'm going to build a table, do I put the whole table in the material testing machine to see how it's going to behave?
I wish.
You wish, right? We could get rid of this whole class if we said all you have to do is build it every time and have enough resources to test it every time. And if it works, it works. If it doesn't, it doesn't, right? That would be a good way to go, all right? That would be a good way to go with infinite resources, okay? So one of the things that we care about is figuring out what the intrinsic properties, the material properties are, okay? So that then we have an idea of the stresses, the strains that the material can handle before it fails or yields, right? We also care about stiffness of structures, so we also want to know what the elastic modulus is, okay? Okay, so there's this, I think I've said it before, I hope I've made it clear before, there's a difference between material properties and mechanical properties. When we talk about mechanical properties, we can expand that to think about what the structure's properties might be. But when we talk about material properties, we're like, just give me a little bit of chunk of this material, and those are material properties that I can then use to figure out what the structural properties will be. Okay, so there's a difference between structural properties and material properties, and sometimes we say mechanical for either. Okay. This is a very powerful concept, right? So then you don't have to put the whole table in the material testing machine, right? You can predict whether or not it's going to fail. And you may think that these back of the envelope calculations that you're doing in this class are just no, I don't know. No, you will want to know these, okay? Because as powerful as the simulation software is, garbage in, garbage out, okay? Which I think you've got an idea of, right? With our examples of doing some finite element analysis in the class. And we'll have one more example where you can do finite element analysis. And what do I mean? I mean that before you do the complicated case, you want to do baby steps, right? So you start with the base case, which you can look up on the internet and say, okay, if I have a cantilever beam, this is how much it's going to deflect. If I have a cantilever beam, this is what the bending stress is going to be. If I have a cantilever beam, this is what the transverse shear stress is going to be. If I have a shaft, this is what the shear stress is going to be when I twist it, right? And then you do the finite element analysis, you confirm that it's good, and then you go ahead and you put your whole table in finite element analysis because you're sure that you've got the right material properties and you've set up the boundary conditions reasonably well, okay? And then you hope, then you say, well, my finite element analysis can't really handle telling me anything about, or I should be careful what I say. It's tricky to figure out what's happening when something fails. All right, so that's where we go back to the safety factors, which we've discussed previously as well. Okay, so We also, in the case of tensile and compressive tests, we're typically interested in relating average, okay, normal stress to average normal strain, okay? And you want to do this with a constant rate of strain. At this point, how many of you have done the lab? How many of you have done the lab? Okay, good. Who has still to do the lab? Okay, all right. Wow, okay. So for those of you who have not yet done the lab, you will have the joyous experience of attempting to make a constant rate of displacement, okay? To get the tensile testing to be more or less repeatable, okay? And in our case, you were turning it and it was like 10 millimeters. We said try to keep it below 10 millimeters per minute, right? And we could also say something in that we could specify a normal strain rate, right? So this is, this is kind of a chance to be like, oh yeah, that's why I did that lab, right? Because I wanted to figure out the elastic modulus. I wanted to figure out the yield strength of the material, all right? And then I could go about and think, oh, okay, this is what's going to happen with aluminum. And then if I'm crazy and I want to do something out of paper, okay, this is how I could go about designing something out of paper, right? So that's what you've been able to do in the lab. Now, for these measurements, we often use something with a constant cross-section, all right? And we usually, when we're dealing with these metals, we assume that the cross-section is constant, that is not changing. Now we know it really is. Why? Because we have the Poisson's ratio, right? But when you're calculating out a stress, okay, over a particular area, and that area changes very, very, very minimally, shall we say, then we just say it's a constant, and it makes our lives easier. When you start using the rubbery materials, then you start to look at things that are not what we call engineering strain, but they're called true strain, okay? And so then in that case, because what happens, right? If the cross-sectional area is decreasing, and you keep the force constant, or for a given amount of force, what's going to happen to the stress? It's going to go up, right, Zach? Yes, it's going to go up, right? So then it becomes kind of consequential, right, as you get to larger strains. But here we calculate our engineering stress, and we also typically use a nominal length or the original length when we're calculating out the strain, and we call that engineering strain. Okay? So, there are a lot of reasons why we should take the data from material testing with a grain of salt, so to speak, in that cliche, okay? Because it's very possible that there are some microscopic defects or something of that, or there could be even issues with the size, okay, of the sample or the conditions, right? So maybe we cut a particular material, we molded it at a particular temperature, and that's going to affect the properties that we're going to observe. And then even during testing, the temperature could have an effect. Usually not so significant for the metals at the temperatures, that we find in our everyday ambient environment, but for polymers in particular, yes, in our kind of normal everyday use, outside, inside, it can make a difference. And it's not completely true. Like in very, very cold water situations, you do have to be, if there's hydrogen trapped in a steel, you do have to potentially be concerned about that as well. Okay, you can have extra brittleness that can lead to premature failure. So if you're a Marine or someone in the Navy or something, and you're working on structures of that nature, you also have to be concerned. Okay, so this is not the first time you've seen a stress strain curve. Okay, and at this point, you probably trust me more when I say, forget about it here. Okay, when we say, is it the proportional limit? Is the elastic limit? Is the yield strength? Look, it's when you take they'll probably emphasize this more when you take material properties, okay? But for our intents and purposes, we're gonna say just use the yield strength, and this is gonna be good enough for us, okay? When you take design of mechanical components and you cover fatigue, you will look more at the use of the ultimate strength, okay? We don't talk about it that much here, okay, but when it comes to fatigue, there are some back of the envelope calculations based on the ultimate strength, yield strength that are useful for figuring out how much or how many cycles of fatigue your sample can take. Okay? And then we've talked in the past also about what happens with brittle samples and what happens with ductile samples, okay? And the ductile samples, they have more of a necking behavior, and there's more elongation before break, okay? And that can be characterized essentially as what is the length at break minus the initial length divided by the initial length, okay? That can give you some idea of how ductile something is, okay? And of course, we have a linear response here, okay? And then we get into the plastic response here. Okay, and we had, for the final exam, it will be cumulative, so, it might be a good idea to have like the strain hardening model, right? We talked about how we have linearly elastic, perfectly plastic behavior, right? That's where it goes up and then it comes flat, okay? And I think you can make a good song, like something like linearly elastic, perfectly plastic, right? The other one's a little more difficult because it's like linearly elastic, linear strain hardening, or linear elastic, linearly plastic, right? But either way, those are kind of the two models that we've discussed, and they haven't really. Exam one did do a little bit on that, I guess. Yeah. Okay. So. Someone or a bunch of people, they go through, they calculate or they measure these material properties, and they put them in tables. And we are grateful for these people, okay? And then people with vested interest in you buying their material, they also give you these material properties, okay? And if you're a material scientist, you're excited about creating new materials. If you're a mechanical engineer, maybe you also are excited about creating new materials, but you're probably more excited about using materials that are available. Okay? Anything interesting? I don't know. I don't have this. I honestly don't have a particular purpose here, but is there anything interesting that you see here in these tables? I have no ulterior motive here. Just wondering if you all see anything interesting. Sure.
Certain materials do not have a ultimate strength listed.
Okay, yeah, so certain don't, and that could just be because they didn't do it, or the data are variable, or this is a page from Wikipedia. Okay, yes, that's not to say that they don't, but ultimate strength can, and you're looking at this one, right? It can be a little bit tricky because cast iron is a brittle material. And so it's going to probably yield pretty close to its ultimate strength. Okay, in that particular case, yes, Federico.
Spider silk has a very high yield strength.
Yeah.
And ultimate strength.
Yeah.
As well as silicon.
Yeah. So, I agree, right? So this we should just be making our buildings out of spider silk, right?
If only.
If only, right? What's the issue with making or having enough spider silk? Yes?
They can only pull, you can't compress it.
Okay, good point. So you can only pull, that's a good point. That's typically true of any type of cable, right? And we see that lots of cables actually go into the use of bridges and other structures, right? Because we put them under tension.
Well, you can, like, it's over the summer I did like a integrity thing.
Uh-huh.
So like, you can use it for the tension members, but not for the compression.
Yeah, that's true. Yeah, and well, I think there's some practical issues with silk, right? Like, even for your clothes, which are not made by spider, right? But spiders, but made by the silkworms, right? I guess silk is not as in the United States as it used to be. Does anyone have a silk shirt? You do? All right. Huh? A bunch. Okay. All right. Well, good. In the 90s, for those of you who might I don't think any of you were probably alive, but maybe some of you were alive in the 90s. Okay, all right. Well, and so then in the early 90s, right, silk was kind of. I remember wearing a silk shirt, right? So, but yeah, production is a problem. Okay, production is obviously a problem. And if you talk to an organic chemist, it's not true. It's not like we can just make and replicate spider silk. Okay, the compound is even though it's something made out from a spider, right? Replicating that chemical formulation is difficult for organic chemists. Okay, was someone else going to say something interesting about these materials? No? All right. Okay, so for my own personal gratification, what is the difference between silicone and silicon? Someone else. Yes, Paul.
Silicone is the rubbery stuff.
Yes.
Silicon's not.
Yes. Right, so silicon refers to the element on the periodic table, right? And it is a wonderful semiconductor material, right? It's what's powering a lot of things in this room right now, right? A lot of things, right? And we can go into transistors and think about how wonderful they are and what they've enabled. Okay? Silicone, as Paul correctly pointed out, is a rubbery material. It still has silicon in it, okay? Right? Silicon is the backbone of the polymer chains, okay? Right? So normally, right, when we have polypropylene, polyethylene, all these others, right? Carbon is the backbone. But instead of carbon, now you've got silicone or silicon in there, and you still have different groups attached to it. Okay? And silicon, or now I'm getting them confused. Silicones are not thermoplastics, right? You have to use a catalyst or some type of cross-linking mechanism to be able to get the polymer chains to intertwine and lock and become more rigid. Okay? Great. So hopefully, when you talk to people and they say silicon, they're saying yes, the element. And when they say silicone, they're referring to, yes, a silicon-based polymer. Okay. So ductility, all right, as I was kind of saying a few minutes ago, can be described in terms of measuring the final length minus the initial length divided by the initial length. Okay, and if you multiply by 100%, you get a percent. Okay, so that's one way of doing it. The other way is to look at the reduction in area. So when you see a brittle material break, okay, what you'll see is that it didn't have much of a chance to neck. Okay, and so the cross section stays pretty much the same. But if it's a ductile material, it like pulls out and it oozes, right, very nicely. Or not so nicely. It doesn't have to be that dramatic, to be honest, to be ductile. With that, right, we have necking behavior and we have brittle behavior. And we just talked about this. And we can write out the percent elongation at break. Okay, and we can also think about what the percent reduction of area might be as well. Okay? And we can report those. Okay, so here's a question. Well, okay. I think I've said it before. For a given material, which is typically stronger, and in particular the ceramics, the yield strength or the compressive strength? Which is typically stronger? Which is typically stronger? Compressive, so a material for example, like the ceramics being compressed.
It doesn't like compression.
Huh?
Doesn't like compression.
So, okay, why do you say that?
Because of the properties of the material.
Okay, okay. All right.
I mean, if you step on a ceramic by itself, it will break because of the shear. It doesn't, brittle materials don't like shear.
Okay. All right, so this, we're actually going to talk about this in just a minute. And the brittle materials, they actually do much better in compression, okay, than they do in tension. Okay, and you can just think of columns, all right, in Athens or in Greece, right, or in Rome, okay. Those they're sustaining lots of compressive force, okay, and they've stood for lots of time, and they did a nice job of making them fat enough, quite frankly, so that they don't buckle. All right, compression, because often when you think, oh, this material is so weak in compression, right? Because I take a toothpick and I do this or something, right? Or I don't want to break. Someone left an ice. Ooh, whose is this? People are just leaving stuff here.
It's all yours.
Their car. I can just take their car.
Who's gonna stop you?
Their ring.
Yeah, who's gonna stop you?
My ethics will stop me. Anyway, so if you're compressing this, right, and it's very slender, and you'll cover this in DMC. Often it's covered in this class, but we're not getting to it. Okay, but if something's very slender, then it's an elastic. It's elastic instability, it's not inelastic. It's an elastic instability, okay, that causes it to buckle out. All right. So typically, materials are stronger in compression than they are in a tensile, okay, loading. And what does it look like on a stress strain curve? So like if you're just thinking, what would the stress strain curve? Because most of our stress strain curves that I've been giving you have been tensile loading, right? They're in quadrant 1 of the stress strain graph, right? But what does compression look like? Well, it lives in which quadrant? 3, right? Okay? So if I'm drawing a stress strain curve, okay, and now I include our friends in compression, okay, what you'll see is that, whoops, okay, that it goes, and this is, there are no numbers here, but it goes down further. Often, this is me drawing, so you can have this behavior, yes, but often it will be a little bit more brittle, okay? It'll be like bam, and that's it. And that's kind of what you see here, right? I'm actually going to just put a little bam. Oops. Okay, like maybe there. Okay, it breaks. So if we begin to now use what we've discussed with material testing, we can begin to create models for failure. Okay? And who doesn't want to know if something's going to break before they use it? At least if they're building it, if they're liable, right? Most of us, when we build things, we just have a sense, right? You get a few 2x4s, you put it together, it's good enough, right? And we're over designing, usually. Okay. But as we go to different applications where you worry or you're concerned about cost and you're concerned about weight, you're going to want to have an opportunity to do some calculations. Okay. Now, these models, we're going to cover essentially 4 models. Okay, we're going to cover 2 today and then 2 on Thursday. Okay, they don't account for everything. Okay, it's very hard to account for everything. Okay? That's why if it's really precious to you, you should do some testing, right? Or inspection. Yes. Well, we're going to tell you when you should use one over the others. Yes. We'll even tell you that today. You get that for free. All right. Okay. In a minute. Okay. Okay. And here it is. If you have a brittle material, use maximum normal stress. Okay. And then on Thursday we'll talk about where did this go? On Thursday we'll talk about something called Moore failure criterion, which is a variation on maximum normal stress. And then we say use caution, because there's a lot of variability, especially with the brittle materials. Okay? But if you're using a ductile material, okay, which is not that's a brittle material, just so you got it, right? Okay? Has anyone watched Karate Kid 2? Okay. Huh? Oh, that's right. There's a new, what's that called? Cobra, yes.
Jackie Chan.
Wait. Jackie Chan is in Cobra Kai?
No, karate.
Isn't that Ralph Macchio? Anyway, so, like, at the beginning of Karate Kid 2, right, it ends Karate Kid 1, and there's some breaking glass, unfortunately. Okay? And it looks very painful. Don't do those experiments, all right? But that glass is a brittle material, okay? But ductile materials, okay, and cast iron, okay, is also a brittle material, even though it's a metal, okay? And it's what you call high carbon steel, okay? But the ductile materials, we're going to use shear stress, okay? And then we're going to use something on Thursday called maximum distortion energy. Okay? And it's nice that the materials that we often care about for many of our structures, I mean, of course, people in civil engineering care a lot about concrete. We do care. We love our concrete, but we don't love the amount of carbon that's required to use it, right? To create it. But we are grateful that for many of the structures that we're looking at, they do use ductile materials. And so we're going to be okay using these different theories. Okay, so why don't you take a few minutes, if you haven't already done it, and answer question number 1. Okay. So this is just a move it to the right category. Okay. So as you're doing this, which of these do you think are controversial? Which of these do you think are controversial?
Epoxy.
Epoxy. Okay. Epoxy. Has anyone used a ductile epoxy? Anyone? Yes?
I guess you could engineer like a composite with the oxygen.
Yeah. I think epoxy is typically, what's interesting, right, is there are 2-part polymers that cross-link that are ductile, but epoxies, those are like the ones you go into. Anyone go into Home Depot and like go right to the adhesives aisle? Always? Isn't that like one of your favorite aisles? You know, you're like glad everything's capped because you know it would smell absolutely horrible if it weren't. Okay. So, what are your favorite adhesives? Huh? Model glue? Or wood glue? Okay. Alright, so like I think, I don't like all the chemicals and how they smell, but I gotta say super glue is pretty incredible. Alright? Yeah, don't, I don't suggest that you use cyanoacrylate on your wounds to close them. Okay, I hate some, like my kids, so like, yeah, you just put super glue on it, right? And close it up. I wouldn't do that. Okay. And then you've got your epoxies, right? Your two-part, right? Some of you are maybe your Gorilla Glue fans, or maybe because that Gorilla Glue is kind of a newer brand, right? And then others of us are more like Scotch, like 3M, traditional. That's the way you did it, or JD Weld, right? Anyway, any other controversial ones that you think could maybe fall in either category? Huh? Are any of these materials controversial? Do you think like you're not sure if it's or could it be both? Could it be? Woo! Okay, so you tell me.
I asked.
You asked. So alumina is ceramic, all right? It's a ceramic form, all right? And it's a nice. It can be a very good thermal insulator. Okay, so aluminum and its pure air form is not necessarily what you want to be using.
What about the mid low carbon steel?
Yeah, mild or low carbon steel. Okay, so this is the high carbon, the cast iron. Okay, so first off, what is the predominant? We have carbon there, but what is the predominant material in steel? Okay, good, right? So we know this. It's iron, right? Okay, so there are 3 on this, okay, that have a lot of iron. Cast iron, okay, high carbon steel, and mild or low carbon steel. So now, if you go to Bing or one of the chat, anyone using Bing now? Yeah, so if you type in, is high carbon steel brittle? The first thing you will see on Bing is no. And then if you go a little bit further down, it'll be like, yeah, it's typically brittle. Okay, it is. These high carbon steels are typically brittle. And cast iron is on the upper end of high carbon. Okay. The mild or the low carbon steels, those are going to be more ductile. Okay. They're going to have more ductile behavior. All right. And I'm grateful for all these materials. I mean, think about how many of these materials, like the first day of class, right, we asked you what were some of your favorite materials, right? How many of these materials do you come in contact every day, right?
The high carbon.
The high carbon? Yeah.
It's knives. No, I'm serious.
Knives, yeah. Yes. So this is one of the things that's interesting, right? Is that the high carbon steels, yes, they are brittle, but they can maintain, they can be very hard, and so we use them for cutting. Okay?
But they're also good if you want to spend money.
Okay, yes, they are good for if you want to spend money, that's true. Often, or if you're a blacksmith or something, right? So the wonderful thing about steels though is they are actually remarkably inexpensive, okay, for what they can do. And they're really nice in that you can recycle them. Okay, you can melt them. It takes a lot of energy, of course, right? But you can do that, and you can they respond to heat. Yeah, so the processing matters. What is the elastic modulus of steel?
200, 20.
100.
Ah, I failed.
Oh, it depends. It depends.
Does it depend? Now you're even making me feel like I failed even more.
After a treatment, you can change.
So elastic modulus.
400.
No, elastic modulus.
Oh, wait, I think it was.
Oh.
No, it doesn't exist.
Oh. All right. Oh, come on. Okay. Question 1A on the final will be, what is the elastic modulus of steel? For half a point.
Actually,
Yeah, I admit. All right. Because I want you to leave this class knowing that. So what is the elastic modulus of steel?
200.
200 what?
Gigapascals.
Gigapascals. All right, there you go. And if you put 210, I'll give you credit too.
I said
All right. So final exam, question 1A.
What's 1B gonna be? Make it 25.
No. What is the elastic modulus of aluminum?
78 gigapascal.
About 70 gigapascals, right? Typically about 1/3 of what you have for steel. All right. And if you look at, I think it's the exam from 2020, you'll see that question 1A was, what is the elastic modulus of aluminum? Because I made a similar deal with that. Okay. Now, but what is the range of yield strengths for steels? All right, it goes all over the place. It can be like 100 to like 1,000, okay, megapascals. Okay, yeah. So that's the beautiful thing about steel is you can treat it, and it can have different hardnesses, and the elastic modulus stays the same. Okay. All right, let's go on. Hopefully you got that one done. Through my talk. Were there any questions? You know, which of these materials I think is very susceptible to, well, there are a few that are very susceptible to that, especially maybe a lot. But at least, which ones are susceptible to kind of what you would find in your home? And I'm not talking torch, and not even like putting it over your stove, because if you put it over a flame, that does stuff.
Gold.
Yeah, so gold, yeah, I would, so the gold, yeah, gold is amazing, right? Because it's actually, well, why do we use it for jewelry? Why do we use it for jewelry? What? Oh,
It's valuable.
okay, and that helps. Yeah, hold on, yes, Graham? Huh? Doesn't tarnish. Okay? And why is that? It's because it's extremely stable. Okay? It's like the most stable material. Now, I'm not saying you can, that it is in ambient conditions. Okay? But it is very soft. Yes?
Oxidized slightly.
Aluminum oxidizes. Gold is going to be very stable. That's why we use it for electrodes. That's why you'll see it for electrodes. Okay? Because it behaves very stably. Silver and platinum are also pretty stable. Okay? Alright? But you don't have a reaction with the gold usually. You know, I guess some people are allergic to gold, but not really many. Okay. Lead, no, lead is, so I don't know the complete answer to that, but lead, I would be okay swallowing gold, not so okay swallowing lead. Yeah, so lead can lead can get into a lot of things. Okay.
Like water.
Like water, or pewters, right? So they use lead to soften them, right? So they do make some. Okay. All right. What I was thinking, latex. Latex is very temperature dependent. Silicone, the rubbery, the polymers are very temperature dependent. Okay. And if you had to choose a brittle polymer, okay, a brittle polymer, which one would you choose? A brittle polymer, which one would you choose? And they're not, they're different grades, so but yes.
ABS.
ABS, okay, I can see it. I don't think of it as super brittle. I think if there's one polymer that I think is usually more brittle than the rest. ABS can, yes, and you can snap it, I agree. Done it, or been around it, right? So yeah, a little bit brittle, especially when it's 3D printed, okay?
Natural rubber.
Natural rubber, no, that's very ductile. Natural rubber is ductile. What's anyone? A brittle polymer. Brittle polymer. It can often take a lot of impact though still.
PVC.
PVC, I don't consider it to be polyvinyl chloride. I don't consider it to be that brittle. It's actually kind of softish, but you know, and if you're sawing at it or whatever. But yeah, it has some brittle qualities to it. I'll take that, especially if it's old.
I was just guessing.
That's a good guess. Yes. Okay, polystyrene. Yes, that's actually probably more brittle than the one I was thinking of. So that's a good one, right? Where do you see polystyrene a lot? A lot of packaging, yes. Yeah. Yeah. Styrofoam is polystyrene in an aerated form. Can someone fact check me? I've been wanting to know if the reason we don't recycle polystyrene is because, or the reason we don't recycle styrofoam is because of because of the fact that styrofoam has such a low density, effective density, it's not worth it. Is that the reason why we don't recycle styrofoam?
It's the cost.
Right, it's the cost because it's so little in such a big area and you gotta transport it, and so that would be my hypothesis, but I don't know. Because you definitely recycle polystyrene. Okay, acrylic is the one that comes to mind as a brittle material. Acrylic. Okay? Polymethyl methacrylate. PMMA. All right, let's go. We gotta go. I'm using your time. Okay. So, here's a failure criterion. Maximum normal stress for brittle materials. Here we go. Okay? So, in brittle materials, failure is often due to fracture. It's sudden. And it's no warning. It just does it. Okay? And here's something that's interesting. First interesting point. The fracture surface is orthogonal to the normal stress. Okay? So you see here how these have like this kind of flattish, sharpish surface. Okay? That shows that it was a brittle fracture. Okay? And if it's a brittle material, well, actually, I won't say that. We'll just leave it at that. Okay? Right? We separate it in this case, right? This is not an actual breaking, right? This is just saying that there's a stress inside, right? Okay? Or maybe it is an actual breaking. What does the Mohr circle look like for uniaxial loading? Like this. Okay? So, and this is, uniaxial loading. So sigma 1 has got a value. And what are sigma 2 and sigma 3? 0. Right. Okay? Because it's uniaxial loading. So what do you care about? Do you care about the radius or the diameter of this circle? If I say we care about maximum normal loading, which do I care about?
Radius.
Yeah, so I guess I care about both because radius and diameter are related to each other, right? I care about the diameter though because I want to know what the maximum normal stress is. Okay? The radius would give me the maximum shear stress, which will be important for ductile materials. But right now we're talking about brittle materials. So I care about being out here. Okay? Now, let's say I have a material that's under pure shear. Are there any normal stresses present in this shearing shaft? Okay. No for an element that is like this, right? Right. If I draw the shear stresses, they look like this, right? And what's the magnitude? It's not so important here, but what's the magnitude of the shear stress? The maximum shear stress, I should say. If I have a torque and I have a C for radius.
C over J.
Yeah, so TC over J, right? TC and J, that will give us the tau xy. Okay. And so this is what Mohr circle looks like. Right? So now tell me, if I rotate an element, right, on the outer surface, can I figure out what a normal stress is? Can I figure out what a maximum normal stress is? Yeah, absolutely, right? It's just tau, right? But moved over to here. All right, and so remember, we know how to figure out the rotation of an element to get us to have a state of principal stress. And we can always get to a state of principal stress, right? So what is, if this was the shear, if this element is like this, how much do I have to rotate? How many degrees do I have to rotate to get, how many degrees do I have to rotate the element to get to a state of principal stress? Is this a bird tweeting? No? I think you were saying 45. 45, right? And some, yeah, so 45 degrees or 90 degrees or more circle. Okay? And this is just me flipping the element. Okay, so now x is this way, right? Because remember, this I drew, right? This is the subscript x is the face, right? And the second subscript, sorry, the first subscript is the face, the second subscript is the direction, right? So this is the x face, and this is in the positive y direction. But if I flip here, right, then I have the x face in the positive y direction on the opposite side, right? Just a reminder. And then now, right, if I rotate 45 degrees, I have a positive normal stress and I have a negative normal stress, right? And that's what you see here. And, you know, if I flip it back, that's what you would see this direction too. So this is often a little bit interesting and confusing, okay? Now, look at this. If I believe what's happening or what I say here, the fracture should happen along a plane that is orthogonal to the maximum normal stress. Okay. And because the material is typically weaker in tension than it is in compression when it comes to a brittle material, okay? We're going to be looking at the one where we have tension, right? These normal stresses are in compression, and this normal stress is in tension. Okay, so now, if we go back to this original configuration, dun, 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 and we have a brittle material. You tell me, what is that fracture surface going to look like? Or what's the angle of that fracture surface going to be? 45 degrees. Okay? Okay, who thinks they can catch a piece of chalk without it breaking before they get it? Okay, Chris Castro. Oh, okay, all right. You trying to help? Okay, we'll go get him, Chris. Okay, all right. I don't know your name, but you ready? Okay. Oh, saved. Saved. I'll try again. All right, here we go. No, that's not gonna. That's all right. I'll try one more time. Yeah. Did you save me?
That was on me. But it didn't break.
Okay, go ahead and get it then. All right. I found 3 pieces of chalk. All right. Max. Max. Oh, I don't think I can get us to the island. Ah! Oh! Alright. Alright. No, don't throw it at me. I'm only allowed to throw it at you. You can't throw it at me. That's like to me. Okay, so those people. Actually, I got a few more. Okay, who else? I'm gonna actually nicely walk it up. You guys. Build character. Build character. No, because I'm breaking my samples. I'm breaking my samples. This is a brittle material. Who else is raising their hand here? You did? You did? Okay. You will need, yes, you will need 2 hands. Okay, Mike, what can we do that? Alright, I did. Alright, good. Okay. So you're gonna take, okay, so after we do this, I should have saved some of this chalk. Okay, shoot. Okay, we're gonna do 2 things. Okay, first, you're gonna take a nice piece of chalk and you're going to apply pure shear. You're going to twist it, all right? And when you do that, take a look at this, and then show some people, take a look. What is the angle of that surface?
Hey, what are you doing?
What is the angle of that surface?
Like 30?
Well, this is about 45, right? Which is what we predicted. Okay, you see that? 45 degrees. Okay. Now, no, don't throw it at me. Okay. Now, if you take, now give one of those ends to your neighbor, because so they can have some fun too. All right. If you take another piece of this chalk, all right, and you bend it, which direction are the stresses?
It depends on where.
Okay, so let's say I'm applying a negative bending moment, all right, because I'm doing a frowny face. If I'm above the neutral axis, is it in compression or tension? Tension, right? And below it's going to be in compression. Okay, but these are normal stresses, right? So what should the fracture surface look like?
Straight.
Should be straight. All right, go for it. Tell me what you get.
Hey.
You get a pretty nice brittle surface, all right? So show your friends. Okay? Okay? Now, who wants to break the big chalk? I've got one piece. No, you guys already got samples, so those of you who already got samples are out. Okay, Chris, I'm gonna give it to you when you're late. All right? So what are you going to do first? Are you going to do pure shear, or are you going to do torsion, or are you going to do...
I don't think torch is going to work.
No.
Try torsion first. Try torsion first. You can do it. I know you can do it.
Believe.
Yeah, you did it. Oh, yeah, okay, that was... Yeah, pretty good. Okay.
It's not very
The people that are clean are not going to be very happy with us. Okay, so... but yeah, he did get more or less a 45 degree. Okay, now can you snap it? Can you bend it? Is it too small?
It's too small.
Too small? Hey!
Whoa,
Whoa, you did it. All right, congratulations. You have broken the big chalk. Okay? So we've had our fun with brittle materials. Okay? I like, when I've done this before, I've used only white chalk. I've got like rainbow hands now. We use colored chalk. All right. So yes, if you twist, this is what you should get. All right, a nice kind of 45 degree surface. Okay, and let's keep going. Any questions on this? Okay, this is the criterion of okay, brittle materials, yes, and it's maximum normal stress. Okay, that's what we care about. Now, there's another way, right? We've used our friend Moore's circle and stress transformations to understand what's going on here, but there's another way of looking at this. Yet another plot. Okay? So, look. If sigma 1 and sigma 2, the principal stresses, okay, in a plane, we're assuming sigma 3 is 0, right? Because in this class we pretty much do that. Sigma 1 and sigma 2, if they are equal to the ultimate tensile strength or the ultimate compressive strength, that's when we think we're going to have failure, right? So you see absolute value sigma 1 is equal to sigma ultimate. This is when we get failure. Okay, so this is the condition or conditions for failure. So on Moore's circle, if I draw a Moore's circle, what do I get? I get something like this. All right, I've got my sigma 1, my sigma 2, my sigma 3 is right here in the middle. I can draw the small Moore's circles inside, but what I care about is whether or not, sigma 1 and sigma 2, where they are relative to the ultimate strengths. Okay, and maybe it should be a little bit more over here for compression than it is over here, but you get the idea. And and you know, we still have football going on, right? I guess college is wrapping up, but
Champions League today.
huh?
There was Champions League today.
Okay, champion something today?
League.
Champion League, okay. Yeah, and there's the NFL and everything. So I kind of think of this as field goal, all right? If you make a field goal between these ultimate tensile and ultimate compressive strengths, you're good. 3 points, okay? In rugby, I don't know, they do field goals too, right?
To try. Well, wait, no. That's a touchdown.
They do some, I don't know how many points they
Just
get.
kick it. I think it's 2 points.
2 points, all right. Right, I mean, one of the great, or actually maybe, right, Adam Korsak, right, the great Rutgers punter, who is gone now, right, and set some records and stuff. But he was a rugby player, right? I think he played rugby in Australia before he came here. Okay, so now that's one way of looking at it. Okay, the other way is to look at it in terms of what's called a sigma 1, sigma 2 plot. All right, so this is going to be new. What do you think sigma 1, sigma 2 means? It means that the axes are sigma 1 and sigma 2. Okay. So now draw in your mind sigma 1 going in the horizontal direction, sigma 2 going in the vertical direction. If you have to not fail, your goalpost becomes a box. All right, you see this? These are the 4 corners. Does anyone play 4 corners when they're in elementary school? All right? So the 4 corners. So the 4 corners are the ultimate strengths, okay? And what you see is that if you're in the box, you're good. If you're outside the box, not so good. And I should not probably use subjective terms like that. If you're inside the box, you will not fail, but if you're outside the box, you will fail. Okay? All right, so we're without a bunch of time, okay, because we've been having fun, or at least some of us have been having fun. Some of us have probably been bored stiff, but others of us have had fun. What you get to do, okay, if you think about a load, is write out what sigma 1, sigma 2, and sigma 3 are, right? And so this is for a uniaxial load, right, with 50 megapascals. And in this case, if the ultimate tensile strength, all right, and the ultimate compressive strength are the same, and they're 100 megapascals, we can see that we're going to be inside the box, okay, right, just like that, and we have no failure. Now, if we have a system that has shear stress on it, it gets a little more complicated. We have to think, what does Moore's circle look like, all right? And will the principal stresses be in or out of the box? Okay. And in this case, what are they? Yes, Chris.
This is for the previous slide, the sigma 1 and sigma 2 plot. Is it always going to be square or can it be rectangle?
It can be, so yes, so tomorrow or Thursday we'll talk about something that is not, it is still a square, but it's off-centered square. And actually and then there's some diamonds that we're going to talk about in a minute. There are a bunch of, and there's ellipses. There are a bunch of different shapes, right? But for maximum normal theory, okay, it's a square. Okay? So this has failure. And then if we look at the sigma 1, sigma 2 plot, we can plot our principal stresses, and we're outside the box. Okay? And if you have a different type of loading, some type of combined loading like this, you do the Moore circle, and you look at what the principal stress might be, and it's just shy of what you would have for failure. So you're barely in the box, barely no failure. Okay? So you'll get a chance to revisit a classic problem, okay, that we've had with some combined loading, right? And look at what the shear stress is. Yeah, I mean, in this case, right? I mean, as a hint, right? Is there any, at location A, what type of stress is this experiencing? Yes. Okay, so it's experiencing, I agree, it's experiencing a transverse shear stress from which load? Transverse shear stress from what?
From P.
From P, right? Yeah, and it's on the neutral axis. Okay, and it's going to experience a shear, right? A twisting shear from TM. Okay? So shear stress that you're caring about, and then we had to figure out what's happening with an equivalent set of normal stresses. Okay, so now, maximum shear stress is for ductile materials. This is going to be applicable to ductile materials, like we just said, and is first kind of discovered in 1868. That's not that long ago, really, if you think about it, right? We've been breaking materials for a long time, but to have theories that were only in the last couple hundred years, right? That's pretty interesting. Okay. So in this case, if you have uniaxial loading, you can see in some samples you actually see what are called Luder lines, okay, and they're at 45 degrees. Okay. And this is the same Moore's circle that you had a second ago, or we had a few minutes ago when we were talking about maximum normal stress. But now, what do we care about? We care about the maximum shear stress. Okay. And we can calculate out what that is, right? It's going to be half of the diameter. Okay. And we have to rotate the element 45 degrees, or we rotate 90 degrees on Moore's circle. And if we think about what's going on, right, we get to a state of maximum shear stress. Now, something to keep in mind, when you get maximum in-plane shear stress, or maximum in-plane shear stress, or optimal maximum shear stress, this doesn't mean that the normal stresses are zero, right? That's the nice thing about principal stress, is that the shear stresses go to zero. Like here, right, in this state of maximum in-plane shear stress, we have an absolute maximum shear stress. We still have normal components, right? And they happen to be sigma average, right? It's the average of sigma 1 and sigma 2. So for uniaxial loading, okay, what's interesting here is that the absolute maximum shear stress ends up being half of the yield strength. Okay, so you're like, wait, what's going on? You're telling me all this time that we report yield strength, but it's really the shear stress that dominates? At least maybe some of you are thinking that. And it's like, yep, that's the truth. Okay? But we still report the yield strength because we know what that loading condition is. It's uniaxial loading. Okay? And uniaxial loading is good for testing both brittle and ductile materials. So it's for ductile material we care. Okay? So when we have uniaxial loading, okay, this is what the Moore circle looks like, and this is what the absolute maximum shear stress looks like. And the absolute maximum shear stress is half, okay, of the normal stress and principal stress. Okay, so this is kind of repetitive, but this may be a little bit counterintuitive. So if on the flip side, right, someone says, here's the yield strength of this ductile material. What is the absolute maximum shear stress it can handle? Boom, you say divide by 2. That's it. Okay? Okay? Divide by 2. Now, if they have the same sign, right, then what you're looking at is seeing if sigma 1, which one's bigger and which one is closer to the yield strength. Okay? if you have them with opposite signs, right? This looks familiar, then we take the difference of them. Right? Where have we seen this before? We saw this when we were calculating absolute maximum shear stress. Why were we calculating absolute maximum shear stress? For this very moment. Okay? Because we wanted to be able to predict whether or not something's going to fail because of maximum shear stress. That's why we do it. Okay? So that's what Moore's circle looks like, okay, in different scenarios. Okay, like this and this. And you could say, oh, this field goal is sideways. Fine. You've got to be within the sideways field goal. That's fine. Okay? Or stay in the lanes if you want. Okay? What does the sigma 1, sigma 2 plot look like? Well, this behavior over here, okay, is pretty similar. All right? So if you're in quadrant 1 or quadrant 3, we have the boxes. Okay? But look, what is this? Sigma 2 is equal or like if I, so let's say if I'm in these other boxes, right? Remember, I have a sigma 2 and I have a sigma 1, right? I can say that sigma 2's got to be less than or equal to, if I get rid of the absolute value, right? Or I can say sigma 2 is greater than, okay, or equal to sigma 1 minus sigma y. Wait, the slope is 1. Slope is 1, right? Between sigma 1 or sigma 2 versus sigma 1, the slope is 1. What does that mean? Boom, you've got a diamond. All right? So instead of it being a box, okay, you have a straight line here. Okay, I am running out of time. We got 9 minutes. All right, but this is the same problem that we just did, okay? But now we're looking at whether or not we have failure due to maximum shear stress. And here we have the yield strength of 100 megapascals. So this does not fail, okay? Why? Well, you could look at it from a couple of perspectives. You could look at it as what's the maximum shear stress that this material can handle? You can handle 50 megapascals. What's the maximum shear stress here? 25 megapascals, right? Or you can look at it as, oh look, this sigma 1 is less than the sigma yield, so yeah, we're good. When you start to get to these types of situations though, where you have shear, right, that's when you start looking at, oh, wait a second, I need to know something about what the maximum shear stress that this ductile material can handle. And it's only going to be half the yield strength. So now our lanes go right through the Moore circle, and this is not a condition where you're going to be safe. Okay? There's a good chance you're going to have failure. And if you plot this on a sigma 1, sigma 2 plot, you're out here. You're outside the diamond. Now, one more example. Here we have combined loading, okay? And in this case, again, we care about what is the absolute maximum shear stress. And you're getting a clue that this is not going to look good, okay? And we're outside the box again, or outside the lanes, and we're going to have failure, okay? So, before the question, one thing to think about is which of these is more forgiving? So now we talked about maximum normal stress theory and maximum shear stress theory. Which has a bigger area on a sigma 1, sigma 2 plot? Which one is more forgiving?
The first and the third quadrant.
Okay, the first and the third quadrant, they might be the same, okay? Okay, in general, which is going to be more forgiving? If you had the same compressive strength, same yield strength and tension, same ultimate tensile strength as the same as the yield strengths, the diamond fits inside the box, okay? And coupled on top of that, that ultimate strengths are usually higher, okay, and I guess I kind of lied a little bit at the beginning. We do care about the ultimate strengths in the compressive materials because they're so close to the yield strengths essentially, okay? And so if you're drawing these boxes, okay, what you'll see is that the maximum normal stress theory is more forgiving than the maximum shear stress theory, okay? So question 3 is another combined loading problem that we've seen before. And you get that state of stress, and then you go about and you say, okay, do you expect to have failure from that criterion? All right? Any questions? Any questions? Okay. So, yes, go ahead. Yes. Because, well, even if the ultimate strengths are the same as the yield strengths, if I bring this out, this diamond would cut from here to here. All right? And so the maximum normal stress theory covers a larger swath of area. Okay? Good. So we've covered material testing and ductility. We've covered maximum normal stress for brittle materials and maximum shear stress for ductile materials. Okay, and now it's everyone's favorite time. Okay, yeah, sure. I'll do that in a sec. Okay. No, don't. Okay, there you go. Okay, so please upload it in the next 10 minutes or so, okay? I need to do that, I agree. Folks, if you haven't picked up exam 1, all right, process. All right. Thank you, everybody, and have a wonderful couple days before I get to see you.
I sent you an inbox for the final exam because the hour.
Hold on.